Hello, my name is Ben Klukshevsky. This is Physics 2212. This is Lab 5, Faraday's Law. Alright, so the contents of this presentation. First up, we'll have the introduction, which will be a description of the lab and the fundamentals. Next up, we'll have observations, data, and calculations, which will be setup, results, and analysis. Third of all, we'll have GlowScript, which will be the actual programmed model. Finally, we'll have a few final questions and a few final thoughts on the matter. Alright, the introduction. So the goal of this experiment is to observe magnet falling through a cylindrical tube of aluminum foil. And using computational models that we produce, we can better understand how Faraday's law explains the generation of current. Alright, a few principles are used in this experiment, main ones being shown here. First of all, we have magnetic flux, which is equivalent to the magnitude of the magnetic field passing through and normal to an area. Next up, we have Lenz's law, which states that the induced electric current creates a magnetic field that directly opposes the change in flux. Finally, we have Faraday's law, which states that voltage is to be correlated with the time derivative of flux. So, before we started the experiment, we measured a few properties for the variables in our experiment. As shown, the aluminum foil cylinder has variables as shown under that column. And the magnet has a mass of 0.024 kilograms, and mu, as found in prior lab, lab 3, was found to be roughly 5.5. So the procedure for this experiment was first to identify the north pole of the magnet. Next, we'd position the tube of aluminum foil vertically and orient the phone to capture movement of the magnet as it falls through the tube. We'd then drop the magnet down the center of the tube, record the time of descent, and repeat to order of 5 magnitude. Alright, a few checkpoint questions. Why can't we use a ferrous tube? Because a ferrous tube can be induced, it could lead to inaccurate values, which would ultimately affect the results of the experiment. What happens to the magnet, and how does this compare to a magnet falling in free space? So it falls marginally slower due to the forces acting upwards, that is, in the positive y direction, on the magnet. So, as you can see, we did the experiment over a course of 5 trials. The average time produced that took for the magnet to fall was found to be an average of 0.93 seconds. So what happens to the magnet? And how does this compare to a magnet falling in free space without a tube? As mentioned before, the magnet now has a slight floating effect, meaning it will fall seemingly slower than in free space. This is because the downward force of the gravity is marginally offset by upwards force provided by the cylinder enclosing the magnet. So what we observed. So this is our computational model that we coded in GlowScript. On the left, you can see a model of the cylindrical tube. The blue area is where the magnet is at the very end of the experiment, at the bottom. On the right, we can see a velocity versus time graph generated by the model. As you can see, time it took for the magnet to fall is roughly 1.225 seconds. So, interpreting the simulation. The intensity of the coloring on the tube indicates the magnitude of the current flowing in each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise and counterclockwise? Red corresponds to counterclockwise that is, and blue corresponds to clockwise. This can be derived using Lenz's law. So what happens to the dynamics of the system when you flip the magnet around? The magnetic force is flipped in direction, but ultimately the magnet will still fall to the tube. So how's the total time in tube of your real-world system compared to that of your computational system? By increasing the amount of tubes in the calculations, the derived values could be improved. Furthermore, you could use better recording equipment and ascertain more certain times for calculations. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? It shows that the magnitudes of the forces fluctuate, but at least at some point in time they're equal in magnitude. So, finally, the what-ifs and whys. What if the resistivity of the conductor were reduced to that as close as possible to 0? How would the dynamics of the falling magnet change? Ultimately, the magnet would fall more slowly. This is because current and resistance are inversely proportional, and the current and magnetic force would grow in magnitude. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The cylinder of foil would contain a lot less rings, and as such, exert a weaker magnetic force on the magnet. As a result, the magnet would fall faster, closer to the speed of actual gravity. Alright, thank you for listening to my presentation. Have a good day.